Hello everyone and welcome to Lee's R&D session number 5, and in this session we're going to be taking a look at noise. Lee?
Yeah, we're going to be doing some noise. We're going to be doing several different noises. We're going to be taking a look at value noise, which is basically taking a bunch of random values and interpolating between them to almost get like a modified sine wave that goes up and down, but it'll be at irregular values. And then we'll use those to layer on top of each other to get what most people would call a Perlin noise, and some people actually do confuse value noise with Perlin noise. So we'll be looking at value noise in both 2-dimension and 3-dimension, and we'll then progress on to Perlin noise. We'll discuss what Perlin noise is and how we can implement it in 2D and 3D. After we get those implemented, we're going to move on to our most complex noise that we're going to be handling in this R&D, which is going to be simplex noise, and we're going to be handling that in 2D and 3D as well. Now, we're going to be visiting a couple of websites discussing the different types of noise. There's some white papers that I've found that we'll bring up, so I'll point you in the direction if you want to do some further research, because like random numbers, noise generation is in a way almost as hotly debated by different people. It can get quite interesting. The mathematics behind it can get involved. I'm going to try to simplify it as much as possible and explain it the best I can so you can see how everything works. And then let's see, what else will we be doing? I've got some examples that we're going to be putting together for the different ones to help you visualize what's going to happen. So with value noise, I've got, I'll show you with a graph plotter how that can be evolved and used, and how it works in both 2D or 1D and 3D. I'm going to show you how Perlin noise comes together in Photoshop. I've got another example, which is probably going to be the best way that I can think of for showing how simplex noise works. And I had to put together a little animation in Maya to help me understand it. So I'm hoping that that little animation will make simplex noise easier to understand when we get to it. Now, the reason why I want to address all 3 different types of noises is each has its own advantages and disadvantages, pretty much with anything. Value noise is simpler to understand, so it's going to be one of the first noises that we look at. Its downside, though, is it can get really intensive processor side. So it's not something that you're going to be wanting to run real time on large textures or anything that needs lots of samples. Perlin noise is a bit more complicated to understand, but it is faster than value noise. But it also suffers from a certain problem as implemented. And when we get to that, I'll show you what that problem is. And unfortunately, I haven't been able to find a workaround for it inside of Perlin noise. But simplex noise, which is the final noise that we're going to be covering, which is the noise that we're going to rely on the heaviest, avoids the problem that we get in Perlin noise, which is mostly if our numbers that we're sending into the noise are perfectly whole numbers.
Mm-hmm.
So if there's no fractional component, well, basically what happens is Perlin noise, if you're sending in numbers that are whole, the way Perlin calculates it is looking for an offset. And if all the numbers that you send in, i.e. if they're all integer values and all whole numbers, you get the same color out for your noise, or same value for your noise. So the entire texture looks a uniform shade of gray, which is not noise at all. So that's an interesting little problem. Simplex noise avoids it. Simplex noise is a faster implementation. It's the more modern implementation that Ken Perlin came up with after Perlin, and we'll get more in depth. But basically, Ken Perlin is the guy that pretty much, well, he did invent Perlin noise. He ended up winning an Academy Award for creating it. And it started off with his initial implementation of Perlin. Then it moved on to what was called the improved Perlin noise algorithm, which is the one that we're basing our implementation off of. And then he did more advanced work, and he came up with simplex noise. And the simplex noise is what we're going to be using heavily. It's also the most complicated out of the three different types of noises that we're going to be playing with. And technically, if you want to look at it, we have a fourth type of noise that we're going to start off with, and that's just the hash, the 3D, 2D, and 3D hashes that we did inside of our random series. Those are technically noise generators if you want to look at it, and we will use them as such. But so we're going to go from the most basic being our random generation of numbers that we've already done, all the way up through simplex noise, and the advantages that we get with simplex noise being speed. Now, if you know about simplex noise and even Perlin noise, you can implement them in 1D, 2D, 3D, as many Ds as you want, 4D, 5D, 6D. Value noise is not as complicated. Perlin noise gets really tricky beyond 3D. Simplex noise, I'm not even going to attempt to try to show you how that works beyond 3D. 3D took me the better part of 2 days to get straight in my head what was going on. 4D, once they start talking about hypercube or the layout of vertices, or the layout of what am I trying to think? The unit cube in hypercube space of 4D. No, can't do it. So it's like going. It's gets pretty crazy.
Okay.
But there are papers that if you really want 4D, you can implement it. But we really don't actually. The other thing is we don't really have a need for it. The only reason why that I can think of that you would want to use a 4D noise is if you wanted to take a 3D noise and animate it over time. And for some academic work and some things like volumetric clouds, that is really cool. But being that we're aiming for an MMO and not a weather simulator, we're not really going to need volumetric clouds that change over time.
Right.
So we'll be able to cheat with 3D noise and call it good.
All right. Awesome. Well, with that introduction, let's go ahead and just jump into the next video where we start getting the project all set up. Thanks a lot, everyone.